So while they're finishing getting set up, welcome everybody. This is a nice turnout. For our last seminar, we had like a dozen pizzas left over, so I'm glad that we actually had enough this time around. So I did cut back a little bit. So thanks to everyone for coming. So this is Dr. Spera. She's joining us from Dartmouth College. She's currently completing her postdoctoral research position. And a postdoctoral position is essentially a research job that you take usually for a year or two, and you've been there for
or 3.
You've been there for 3 years? Okay.
Yeah.
2.5?
2.5.
2.5. Okay. And this is the sort of thing that you do after you earn a PhD. And so typically there's soft funded, meaning it's like grant money that's used to fund your position. So she's wrapping that up, and then she is heading to
University of Richmond.
University of Richmond. So she's going to be starting a tenure track assistant professor position, and she's going to be actually moving there in December. So with
I'm
that,
gonna miss the snow.
you're going to miss the snow. Okay.
I'm not looking forward to the humidity.
I think it's recording, I'm not sure.
I'll start because I do a thing where I generally make too many slides anyway. Okay, I'm just going to talk about the background, which might be a little bit longer than usual, but I do something. I do a lot of my work in Brazil, so I'm going to talk a little bit about why that's important. I'm going to talk about the approach I use. I'm going to talk to you about regional climate modeling and just basically how I've been struggling for the past year. So this is a talk where I'm just going to complain about my research, so I'm really looking forward to it. And then I'm going to give you some concluding remarks and just talk about how I sort of got to where I am. The things that I think about most, I really think about this question, which is how do we balance human needs and ecosystem function? So I'm really interested in human environment interactions. That's why I'm in a geography department. And I think about how we manage our landscapes to balance human needs with ecosystem function. So I think about local, regional, and global biophysical and social processes and how they manifest themselves as changes in land cover. And I'll explain what that means in a second. And then I think about how those changes in land use and land cover sort of feedback and affect local, regional, and global forces and processes. Wrong way. And when I think about these questions, I use a bunch of tools to answer these questions. I use a lot of satellite data. I use regional climate models. I use GIS. I use spatial statistics. And then you'll see throughout the talk, these are all tools that help me get at disentangling these complex relationships. So I focus a lot of my research in Brazil. And today, the specific human need I'm going to be talking about when I talk about human needs and ecosystem function is agricultural production, food. I'm going to talk about food. And the ecosystem service that we're trading off for it generally is maintaining the regional water balance. This is Brazil, in case anyone was unsure. So the different biomes of Brazil, so the different vegetative regions, are shown in different colors. And Brazil is hugely important when we're thinking about balancing ecosystem function with human needs. And I like to show these charts because they sort of conceptualize pretty well how I think about these trade-offs between different ecosystem services. So these flower diagrams, all these axes, the longer the petal, the more that you get from that ecosystem service. So if you're a natural ecosystem, if you think of just the natural Amazon rainforest, undisturbed, it does a really good job at regulating water flow, water quality, it sequesters a lot of carbon, it regulates climate and air, provides habitat and biodiversity, forest production, infectious disease mediation. But if you have natural forests, you obviously don't have crops. That's why that crop production petal is really, really small. If you think of the inverse of this, maybe that's intensive cropland. So if you clear forest and you put crops there, which is what happens in a lot of Brazil, all of these other petals, you do not have forest production. You have less water flow regulation. You're not preserving any habitat. You cleared the habitat. And instead, you have this big, your ecosystem service that you're maximizing is crop production. So I try and think about how do we get this? How do we get flower petals everywhere and make a nice symmetric flower where all the ecosystem services are met? And basically, Brazil plays a huge role, and I think many people don't realize this, in our world agricultural production. This graph is a little confusing, but I'll walk you through it. So this is the percent of global production that Brazil accounts for, and this is the percent of global exports that Brazil accounts for in all of these crops. You have orange juice, sugar, soy, chicken, coffee, meat, beef, pork, maize. I just picked the ones that were 1, 2, 3, 4, but they're in the top 10 of a lot of them. So I don't know if people realize this, but over 90% of the 80% of the orange juice exported around the world comes from Brazil, and they produce over 50%. I mean, we get ours from Florida generally, but when we can't, we get it from Brazil. So it's a really important region if we're thinking about places like global food security, and it's important because Brazil is often talked about a lot when we think about carbon sequestration and regional climate. So most people think that the land from this agriculture is coming from this biome, the Amazon, which we all know pretty well. And we picture things like this, forests on fire, big agricultural fields. But if you look at deforestation, so this is area deforested every year from 2000 to 2017, in the Amazon, you actually see that deforestation rates have been decreasing. At the same time, we see that this is area planted in millions of hectares of soy and sugarcane. We see that soy and sugarcane planted area have been increasing at the same time. So where is this land coming from? Well, it's actually coming from the biome that I study. It is near and dear to my heart, called the Cerrado or Cerrado, and it's their savanna biome. Most people don't know about this, but it looks like this is the shape of it. It's a biodiversity hotspot. There are more endemic species in this biome than there are in the Amazon. It stores about half of the carbon that the Amazon stores, and half of it has been deforested. So all of these gray areas are regions that have been cleared. And if we just toggle back and forth over the last 16 or so years, so this is the regions that have been cleared since 2002. A lot of this has been cleared for pasture in the 70s. And today, you actually see that what was left of these little yellow was left of the Cerrado, especially if you focus on this region. You see that there's been a lot more clearing just in these 16 years. In fact, there have been over 5.5 million hectares of land cleared just in these 16 years. So I lived in Rhode Island for a long time. When you live in Rhode Island, you measure things in the size of Rhode Island. So this is about, do I have the right number? 18 Rhode Islands in 16 years. Clear. Okay, and if you're not supposed to like compare yourselves to others, but if you compare the clearing of the Cerrado to the clearing of the Amazon, the Cerrado has been much more decimated by clearing. So much so that it has been referred to in literature as a sacrifice zone, in that the Brazilian government sort of understands that the Amazon is well known and has a lot of carbon, and they know that the Cerrado is sort of less well known. So they're in the geographic, like humanistic literature, people have talked about the Cerrado being sacrificed in order to save the Amazon. And today there's still 37 million hectares of Cerrado legally clearable because there are totally different laws regulating how much you can clear in each of these biomes. Okay, so how do you even understand what's happening? The Cerrado is bigger than Alaska. So how do you even understand what's happening at this scale if you don't want to drive around, which I've done before, on really sketchy roads, with just a GPS and try and make some maps? So remote sensing and satellite data are really great tools for mapping land cover dynamics across large spatial scales. You guys are like, I thought you were going to talk about regional climate. I'm going to get there. There's a lot of history. Okay, so this is the satellite data that I use all the time, and it's called MODIS, or it's called the Terra satellite. It's the MODIS instrument, the Moderate Resolution Imaging Spectrometer, and I use one of their products called the Enhanced Vegetation Index. But really, we can just think about this as this measures greenness. The satellite takes a picture, takes some data, and it just essentially tells you how green something is, how green that land it is scanning is. So the EVI ranges, you have your pixel, they can go from 0 to 1. And if it's a 0, that means it is not green. There's no photosynthetic vegetation there. If it's a 1, that means it's super, super, super green. There's a lot of photosynthetic vegetation there. And so these are typical data scenes of EVI. So I've sort of mapped it. So because these are just black and white, anything that's black is low vegetation, so it might look brown to our eyes. And anything that's white is super high vegetation, so it looks green to our eyes. So these spindly things are agricultural fields. They only plant agriculture, and it's generally soy, during the wet season. So we can see that in the dry season, they're black. They have no EVI, they're just barren fields. Whereas in the wet season, when soy is thriving, they're bright, bright green, right? Because the satellite can sense this from space. So what you can do is you can stack up all of this data and see how changes in greenness differ over time. So I can look at this pixel and be like, oh, what is happening with the greenness here throughout the growing season, which is the inverse to ours because they're in the southern hemisphere, so they grow between our winter. So this, I'm like, oh, there's not green, and then there's a jump in greenness, and then a jump in greenness. Like, what is that signal? Here, whatever this pixel is, it sort of greens up and then cools, then comes down. And that occurs, this green up occurs, these blue bars are the rainy season, sort of greens up with the rainy season and then drops. And here we see these very big jumps in greenness. So I can take a guess as to what these shapes actually mean and represent, but to actually know what's on the landscape, I have to go down and fly around in terrifying crop planes and go around with the GPS and go to all of these points and be like, what are these signals? So when I come back to my computer, I'd be like, okay, I was here, I know this lat long. This, it had this shape. Now I know that this shape was a soy and corn rotation. Or I was here when I was out in the field. I went there, oh, it was Cerrado, it was natural vegetation. So what you can do is you can look at all these different shapes. And it's really nice because the agriculture in Brazil is just this large scale mechanized agriculture. You're literally driving around and it looks like Kansas, except for there's palm trees in front of the field. So you're like, okay, this is not Kansas, but the fields are huge. You can't see the end of them. And they really only plant a few things in this large scale agriculture. They plant soy, they plant corn, and they plant cotton. And they plant them in very specific orders. Soy always comes first, cotton always comes second, corn always comes second. And they each have these signals. So what I've done is I've created an algorithm that will basically take all this data, ingest it, understand these relationships and different things, and then spit out the land cover. But once you do that, and that literally was my dissertation work, and took like 4 years. And then you have to go down and prove that you were right. So you have to go back and drive around again and make maps and make sure all your maps were right. But I got to take an undergrad with me last time, so that was great. Her name's Clara. But the result of that are these annual maps of land cover, which you can then use, and I use in a regional climate model, to parametrize, to try and understand how deforestation and replacing natural vegetation with agriculture actually affects the regional water balance. So we're going to focus on this region right here because it has had the most clearing most recently. They call it Mato Piba because it's the states of Maranhão, Tocantins, Piauí, and Bahia. They sort of do this like 16-year-old girl thing with the designation, but they call it Mato Piba. And there have been huge land use changes here in the past 15 years. And 95% of the agriculture here is rain fed. So the farmers in this region are really dependent on knowing when the rains are going to start, on knowing that they're going to occur for the entire growing season, and knowing when the rains are going to end, right? Because their wealth, their money is dependent on this stable rainy season. And as you guys have probably learned in many of your classes, we know that vegetation plays a really important role in modulating weather and climate, right? So if we think about a really hot day, if we're in a parking lot, that's going to feel really differently than if we're in a forest, right? And here, this figure kind of tries to show what happens in Brazil. So if you have your natural ecosystem, which is this half, you have these trees that take water, they take groundwater, they evapotranspire into the air, that gets recycled as rainfall. And then the trees intercept that water, they take it back up, a little bit of it goes to runoff. Once you clear that land, you have no trees on your landscape, no vegetation with deep roots that can recycle that air and evapotranspire it. And so then you expect decreases in rainfall. We've seen increases in storm runoff. So you can imagine a world where the farmers actually clear so much land that they disrupt this system so much that they actually don't get the rainfall they depend on. Over half of the rainfall in Brazil is recycled. So it's really important to keep the system intact. So the first thing I did, though, was ask, does this matter? If you clear land, do you actually see a signal at all? So this is MODIS data, but a different type of MODIS data. It's evapotranspiration data. And here I've colored it. So blue means that there's a lot of water being recycled back to the atmosphere. So high evapotranspiration rates. Yellow is somewhere in the middle, and red is really dry. There isn't much water being recycled back to the atmosphere. Low evapotranspiration rates. So I just took this screenshot. This is the actual like RGB land cover image, and these are all these fields, right? So these blocky areas, these rectangular areas are agricultural fields, whereas these darker areas are the natural dark vegetation. Unsurprisingly, if you overlay these you'll see that this is taken during the dry season. There is a lot less evapotranspiration going on over the fields than there is over the natural vegetation. And we can quantify this, right? We can look at average evapotranspiration rates over the whole year. And I did that. And it turns out that between 2000 and 2013, there was actually a 26 millimeter per month average difference in evapotranspiration rates over agriculture than over natural vegetation. And if you look at this graph, so this is evapotranspiration in millimeters in each month. The green bars say how much is occurring over the Cerrado, while the orange bars say how much is occurring over agriculture. You see that that difference is really, really stark during the dry season, right? Because the natural vegetation of the Cerrado has these deep roots that can access deep groundwater sources that allow for evapotranspiration during the dry season, whereas if you have a field, there's no vegetation there to actually put water back up into the atmosphere. But during the wet season, when you're managing your crops, you almost have similar evapotranspiration rates as natural vegetation. So I thought this was interesting. And I thought, hey, maybe this difference actually means something when it comes to precipitation. And in talking to farmers in Brazil, which I do sometimes, they say that they've noticed a difference in the start of the rainy season. They say that they think the rainy season is less stable. And they also say that they're starting to think about irrigating from the rivers more to compensate from these differences that they think are happening in precipitation. So now I'm going to get to the regional climate model. So to answer this question, okay, so we've observed that there are changing land cover, that changing land cover results in changes in the water budget. Okay, so why though? What are the physical mechanisms controlling us? How much has changed? How much has this land use change affected the water budget? This is where a regional climate model comes in. So I use NCAR's weather research and forecasting model, adorably called WRF. So I'm going to call it WRF the rest of the time. I'm supposed to put a Star Trek reference in here that I don't understand, but if you understand that, I guess there's a character called WRF. Okay, so with this climate model, which has a representation of the land surface, has a representation of multiple levels of atmosphere, theoretically it should be able to understand, create, model, and predict interactions between changes in the land cover and the atmosphere. I want to ask this question. But the first question that we have to ask is, does this model even work over Brazil? It has not been used in Brazil that often. It's generally used in the United States and Western Europe. South America is pretty problematic when it comes to climate modeling because it is this tiny landmass surrounded by tons of ocean, and on the west side of it is this huge mountain range. Regional climate models hate mountain ranges, they hate boundaries, they really don't love this ocean, giant mountain range, small landmass, ocean gradient. They don't perform as well as you do if you were working over like the Great Plains. So the first question I had to say was, does this even work? Here's the other fun thing about climate models. There are all these different ways, a bunch of different combinations of things that you can choose for different types of maps. So there are 15 options for how do clouds work. There are 10 options for how does rain work. There are a bazillion options for how does the atmosphere and land interact. So a really fun part of climate modeling is putting all of these together in a bunch of different scenarios and being like, what happens? I got the Amazon to freeze like 3 times and it was not a great situation. Literally going from here to finding something that sort of worked, that's another 6 months of your life, am I right? But eventually you do all these scenarios and you find a combination of all of these things that at least well enough, statistically okay, represents, can accurately predict past climate, right? So you're like, okay, how's this thing working? It can simulate what's happening over Brazil. Great. If you notice from this figure, we just completely ignore the fact that it can't do the Andes and I'm the only focus on this box. So, okay, the other thing about the WRF climate model is it has this baseline regional land cover map. It has a default, this is what I think the world looks like. And this, obviously, this orange is water, the colors mean nothing except for the fact that they're different land categories. So every different color is a different land category. Having worked here a bunch, I know that these 4 land cover categories that are in the area I'm interested in, the fact there are only 4, that is way too simplistic. Then another thing I had to do, super fun, is actually put those land cover maps that I made and talked to you about earlier in the climate model, right? I wanted to use more accurate data, an improved land cover surface to see if that would affect the ability of the model to recreate climate in the region. So the first thing we did was we were like, okay, does this even matter? Does land cover matter? Does the WRF model representation of land cover matter if we're trying to simulate climate? And not only do you have to change the land cover, this is like just months and months of digging in code. And I'm not a computer scientist, so this has been a wall sort of thing. But you not only have to change the land cover, but you have to actually tell the model how to grow crops. Okay, so this green line here is satellite observed greenness. So this is like what's actually happening on the landscape and places where they grow one crop and places where they grow two crops. Okay, the blue line is what I eventually forced it to do. The magenta line is what this one, this line is what WRF assumed every picture that it marked as agriculture was. Just this big curve in greenness. And then WRF also has this thing where it's like, we're going to try and grow crops on our own. And these are these dotted lines. Not great. I think they're trying to grow wheat. Okay. So then the first thing we did is we basically did a bunch of model runs for 10 years with their original default land cover surface, and my like, hey, this is more accurate, I think, land cover surface, right? And these are the results of that. It turns out when you put in a more accurate land cover surface, the model is able to simulate climate more accurately in the past. So these graphs there's a lot going on, but basically this is precipitation. The darkest bars, these darkest box plots, but that's the observed data. The middle ones, the middle color, that is the result of of the improved land cover data sets. And these lighter colors, that's the default land cover. So the model does really, really well, actually. Every time there's a yellow bar, 2 yellow dots, that means that they are mapped within 95% confidence intervals to the observed data, to the historical data. The model, as you can see, because there are 2 dots on all of these, on most of them, the model actually does a really, really good job at simulating or modeling, predicting the seasonal cycle of precipitation. But in months, with the improved surface, with a more accurate one, it gets more months right. There are some where there's just 1. So it actually gets more months right when you use a more accurate land cover surface. And we looked at this for evapotranspiration, and we looked at this for temperature. Same thing, darker colors are observed, middle colors are that improved accurate one, and then the lighter colors are the default land surface. And the improved one gets more months right out of the year than the default one. You're probably saying, wow, the model really does not do a great job of simulating temperature. There's a cold bias throughout the whole model. And it also overestimates evapotranspiration during the early part of the growing season across all models. But the improved land cover one sort of gets these dry season months right, which I think is important. I spent a lot of time trying to figure out why the model was so bad at evapotranspiration in September, October, November. You can see that observed evapotranspiration in October is around here. This is the modeled one. It's putting 4 times as much water back in the atmosphere than it should be. And that turns out their soil moisture model is not great. So we broke down the components of evapotranspiration over time. So this is ground evaporation. This is evaporation. The blue is evaporation of intercepted water, and the green is transpiration. And you see that big overestimation of evapotranspiration is due to the fact that it really overestimates ground evaporation. There's something in the soil moisture model that's incorrect, and the digging I've done has not really, I don't know how to fix it. That's like problem number 1 of all the problems I'm about to talk to you about. Okay, but from this work, this like little bit of work, we saw that if you actually put in a more accurate land cover surface, you do see improved model performance across all of these variables, especially in the dry to wet season transition, which I'm most interested in because that's where we see those greatest decreases in evapotranspiration. And that's when the rainy season kicks off. You need water in the atmosphere. Okay, yep. Those are boring. Great. Okay. So what is next? We know this thing works in Brazil. We know there are problems. I really wanted to set out to ask the questions. I really want to answer the questions I set out to answer, which is like, does land use change actually affect climate? And it has been a solid another year of me trying to get this model to do what I want it to do, and it is not working, and this is where I super complain about it. Okay, my two problems. I did a thing where I decided to use two different versions of WRF to try and do two different things. So WRF releases a new version like every year. I did this with WRF 3.7. So there's one where I'm trying to actually just do that thing where I force the model with vegetation. But the newest version of WRF thinks it gets this, I can grow crops better. And I think it'd be really interesting if it can grow crops, that interaction between crops and the atmosphere. I'm like, okay, I'm also going to mess around with the climate model. I'll also mess around with the crop model. And I'm going to do both things at the same time because when one upsets me, I'll just do the other thing. That's basically where it's going. Okay, so let's talk about me trying to force the land cover, not letting WRF grow crops on its own. Okay, so this is a graph. So I created three different scenarios that I used in WRF. I did one where I forced the land cover to be Brazil, all natural vegetation, as though we have never touched it. I did one where I cleared, and that's anything in the black line, those are the results from that scenario. The blue and green lines are the same scenario, just different runs, where I said, let's clear the entire Cerrado and put agriculture there. So no Cerrado left, all agriculture. And then the red and yellow lines, like Gryffindor colors, those are the simulations where I put Brazil in its land cover in 2016. It's like what everyone has done now. Okay, so this is a graph of the results. It's evapotranspiration over time. I did a lot of things to try and fix this. I halved the amount of water the soil could hold. I changed how quickly soil could evaporate from the ground. I've tried multiple ways to compensate for this situation. But this is evapotranspiration over time. The black line is the top one, and the other scenarios are the four that are clumped together. This makes sense based on what we've seen observationally, right? Natural vegetation, that black line, is putting a lot more water back into the atmosphere during the dry season, whereas these other land scenarios aren't. I'm like, okay, great, that makes sense. Let's keep working through this water cycle. Okay, thinking about runoff now. This black line here, that's with Brazil, all natural vegetation. These four are the other, like single cropping in 2016. I'm like, okay, yeah, this also makes sense. If there are tons of trees with roots, then all of that water is going to stay in the system and not leave through runoff, right? And this we've also seen in observed data too. I have colleagues who work in streams in Brazil, and you see that in deforested watersheds, stream flow increases 4 times faster than it does in a forested watershed. Like, okay, these two are jiving. I cannot wait to see that signal in precipitation. I cannot wait to publish a paper saying we should stop clearing land in the Cerrado. And nothing. This is my presentation graph. They're all the same. This is problem number one. And then I did out the water cycle math, like precipitation minus runoff minus evapotranspiration, and obviously it's just going to tell you what these three graphs tell you. So what I'm hoping, I've only run these simulations for 5 years. This is a graph of average soil moisture over time. I have 4 different soil types. This is for everything in single crop rotation. So as you can see here, soil moisture is decreasing. I don't know if I haven't dug up the data to see if in the natural vegetation, the soil moisture is also decreasing. Because what could be happening is that all this is doing is it hasn't run long enough, but it's actually just depleting soil moisture stores. Like potentially, my little bit of hope here is that if I run the model for 15 years and the soil moisture storage is not being depleted in the natural vegetation scenario, but it is in all the other scenarios, then maybe I'll see a signal in precipitation. But it takes a week to run 5 years, so I'm still doing that. That's problem number one. When I get frustrated with this work, I try and make crops grow. That's really fun. Okay, so this is old WRF. It's really awful at growing things. New WRF is like, we can grow stuff in the US, let's use this crop model. And here's some proof. This is a map of, it can actually tell you how many grains are grown in crops in the US. So it's a graph of grains, like grams per meter squared. You see a jump when corn is grown, you're like, oh God, this works so well in the US. Isn't that great? They have all these maps of growing degree days. You have to put in a lot of information to make the crops grow. Put in growing degree days, you have to put in when the planting date is, when the harvesting date is. You have to tell it all of these things that I foolishly just assumed that the model had for the entire world. Fun fact, they only have it for the United States. So basically, months of modeling, coding, creating new maps of growing degree days, harvest dates, all of this stuff. Oh, I set this up incorrectly. But I learned that it was only set up for growing these in the Northern Hemisphere. Literally in the code, it did not allow you to grow something in the Southern Hemisphere summer. So I had to learn Fortran and code like, hey, just shift it 6 months, please. Like, let's acknowledge that the Southern Hemisphere is a thing. So that's cool. Okay. There's no data that just comes with the model anywhere outside the US. Like none at all. So I created that data, you can create it, that's fine. It's just GIS, spatial statistics, all that stuff. And there are all of these weird things that are literally hard-coded into the model as just numbers. Like I realized at one point that for some reason, all of the growing degree days are being divided by a number 1770. I was like, what is this number? Why is this? It's just a number that's in all of the code. And it turns out that's the average growing degree, the average seasonal length of growing, like average growing season growing degree days, the average accumulated temperature during the growing season in the United States. This is going to be very different than the tropics because it's way hotter and gets sun all the time. So we had to deal with that. So basically, my new paper topic in my head, that because I'm now in a geography department and I'm thinking critically about things, is I really actually want to write a paper about how this climate model is actually racist, right? Like the creation of knowledge. I'm serious though, because if you think about it, Western, Northerners, people in the United States are creating this knowledge. We're the ones in power. We have the tools to use it. People in Brazil or other countries in the global south that could actually benefit from regional climate models cannot, I'm not that smart, but I know what I'm doing a little bit, and it's taken me forever to just drill through this code. So I think as I'm getting frustrated with both of these projects, I'm going to actually work with some critical geographers in my department to think about the construction of knowledge and power and how technology sort of created in the global north and how it's not really translatable in the global south. This is my name, I'm throwing it out there. Let me know if you think it's a good idea, bad idea. Okay. So yeah, I'm currently working on both of those two things all day, every day, all the time when I'm not teaching. And that's why my postdoc has been 2.5 years. And I think I'll just conclude by telling you how I got to where I am. So I did earth science as an undergrad. I did not do meteorology, but I did earth science. And I studied a lot of rocks. My advisor was the guy who drove the Mars rover, which is very cool. Yes, I get it. I wrote a senior thesis on literally how light interacts with sand grains in Alamogordo, New Mexico, because the sand dunes there are actually an analog site for a site on Mars. So I learned how to use satellite data, I learned how to use spatial analysis, and after that year, I was like, who cares about this at all? I was done with, I needed something applied. I needed people to be involved. I did not care about the lights and the rocks and the sand grains. I just needed something else that would make me care about the lights and the rocks and sand grains. So, but I knew how to use satellite data. I knew how to upset planetary scientists. I knew how to do spatial statistics. So then I applied to a grad program that actually, I found a new program. It was interdisciplinary, where I was co-advised by a Mars remote sensing scientist, but also a quantitative sociologist. And it was, my whole dissertation was on mapping and monitoring land use change in Brazil, making those maps, which is where the remote sensing scientist came in, but also understanding the drivers of that land cover change using spatial statistics and things like that. This is me in Brazil in a town called Lucas do Rio Verde. They have this big pig there because this town kills more pigs and grows more corn than anywhere else in Brazil. And they dress them up in different colors every year. But that's how I got to Brazil. And then as a result of my dissertation, I was using all this observational satellite data. I'm well, we see these things happening, but I can't actually get at the physical mechanism for them. So as a postdoc at Dartmouth, I've been learning how to climate model and learning how to use WRF and hitting my head against the wall, and then hating this research situation. But I do want to add that I have gotten to go so many cool places and do so many cool things through this degree that I never, ever, ever would have done otherwise. So I just like encourage you to stay in our science. And if you have any questions about that very quick tour through my research hell for the past 3 years, let me know. Yeah, that's it. Your question.
Question. I'm just having some.
Yeah,
Can I ask a question that's not related to this?
sure.
What part of Rhode Island are you from?
I went to Brown, so I lived in Providence for a while. I'm from Brockton, Mass, which is not Rhode Island, but I'm from Providence. Yeah.
How good are the weather observation data?
How good are they?
Yeah, like in Brazil.
Yeah, not great. So like, I compare the model data to crew data, but crew data are based on interpolated weather observation data. And there may be 3 points that they're interpolating between to grid the entire region. So it's not as well, so it's not great. One of the new things I'm thinking about doing, so farmers have said like decreases in precipitation, all of this stuff, but no one's actually looked at whether or not that's the case. And precipitation data is very hard to like get a trend from, right, because it's very noisy. So I've reached out to colleagues to try and get one station's observational precipitation data. And then I'm also thinking about if Princeton has a allegedly like better gridded precipitation data set to see if there really if there has been a change in precipitation. Like maybe I'm searching for something that doesn't exist, right? I really don't want to publish a paper that says clear cut, go ahead, you're doing it right. Like ethically that makes me not feel great, but I've also been publishing papers about nothing for a while, so. Yeah.
Have you notified UCAR about the problem with work?
Oh.
Northern Hemisphere?
Me and WARF people have an email chain going back. So the whole land surface model is one guy. His name's Michael Barlage. And this works way better in the US than it does in Brazil. And it's used more often in the US than it is elsewhere. And so I think I am lower on the priority list than other things. But I like honestly joke with my advisor at Dartmouth that they have a special inbox for me. I send so many emails.
Did you run those models at Brown?
No, at Dartmouth. I only heard it all at Dartmouth. Yeah. They have a cluster there. Which
At Dartmouth?
Yeah, Dartmouth.
Yeah, the big center at Brown. You weren't there.
Oh, no. Yes, I did not take part in the computational stuff at Brown. I mean, I did my background. What did you do that?
There's a center at Brown, and there's a woman there who worked on I think microphysics and worked at UCAR. She's now in that center. I believe you might want to contact.
Do you know her name?
Kershaw, maybe?
All right.
I'm not sure, I don't know, I wasn't there.
Yeah.
But she's, she may be able to help you. She
Okay.
has access to Oscar, that's their.
Yeah. That is their supercomputer.
Right.
I use my own. I never
Sure,
attempted
sure.
off.
But you might be.
Yeah, I'll.
Look up CCV at Brown.
Yeah, I will.
Helen K. Ellen the
I'll
K.
Google. I'm a good Googler.
And she was at UCAR, I don't know her at all.
Okay.
But, and she worked, I think, on microphysics and work. So she might have something.
Yeah, I don't think she must not have, she's probably the physics or applied math department and not in earth science, is what I'm thinking. Also.
Maybe she was at UCAR and then she went to the center.
Okay, I'll try to find her. Yeah. No, you.
Great presentation. Just curious what provided your initial condition and boundary conditions for the model.
Year right interim analysis. Yeah. Mm-hmm. Which I haven't checked to see if that's also problematic. I'm just assuming it's not.
Like, so that provided the moisture estimate.
Mm-hmm. And it's also difficult because there's a lot of, there's like not many places where I get validation of flow moisture data in Brazil. There's a few stream flow gauges that you have to like aggregate over the whole watershed. So it's the easiest thing if I could look at are precipitation temperature and evaporation transpiration. I wish there were just like map data is too new and I don't know how accurate, yeah. But great. It could be It's been a thought of mine, I just have avoided. Yeah. Yes. Oh, yeah. Yes.
So you're talking about like large scale deforestation. So would that also affect the topsoil amount since the deep root zone can't hold that?
Great question. Yeah, so it actually turns out, so one of the farms I work at in Brazil, so they got that, right? They got exactly that. You expect this crazy soil erosion. So the farmers actually built all of these, they started building wooden rows to stop it from going to the soil. But because the soils are so sticky, they don't move. Nothing moves. Phosphorus doesn't leach out into the streams like it does in the United States. Nitrogen doesn't leach out into the streams like it does in the United States. My colleagues who work on the riparian zones, because they expected with all the fertilizer, that stuff to end up in the stream. The biggest differences they see actually are extreme temperature, and that's affecting like the macrobiology. But things haven't, there have been different effects because the soils are so depleted of phosphorus that anything they put on the soil actually sticks. It's like super clay and nothing is moved. They ripped out all the wooden fences they initially put in to keep the soil in place because they're like, it's not moving. I don't know if that's true of the deep Amazon, but in that transition zone anyway, where it's mostly obstacles and stuff. Yeah.
So you had mentioned the 50% recycling of the water.
Yeah.
Which I was surprised at how high this is.
25 to 50.
Okay, so does this mean that 50% of the precip that falls is coming from the land, or does it mean that 50% of what comes out of the land then stays on the continent and falls as precip?
That one.
Okay.
50%. As I understand it, half of what goes up doesn't move that far and comes back down.
Comes right back down.
And like the other thing about the Cerrado, there have been a few, I think Spracklin was who did this study, but he looked at back trajectories of air masses bringing water to the Amazon, and it actually the air masses bringing water to the Amazon actually pick up most of that moisture in the Cerrado, so that's really important.
So just an observation that I find this really remarkable that not only are there data gaps, but there's also huge modeling issues as you've been able to show. And I guess I in my own head, I've underestimated the importance of the interaction of land, because you think about the ocean as being so incredibly important. And that's theoretically more accurate with our GCM and projections. But just thinking about how important this is, it really makes me wonder about our climate change projections, how accurate they may be in regions like this.
Yeah, and like if you look at like an IPCC report, if you do if you look at South America, when they do the averaging, they're like, this number of models says predict wet, dry, whatever. In most other regions, a majority of the models agree. South America is where you have the most mixed, like plus minus on precip and stuff like that, especially because it's controlled by North Atlantic temperatures, El Nino, like the PDO. There's so many things that are affecting the small landmass that it stores so much carbon, right?
So there's like there's a large model spread either way in this area.
Yes, totally.
What you're trying to get at.
Mm-hmm. And those are with the big global models, not with these regional things that
of course.
Yeah. Yep.
Regarding the deforestation and agricultural land use, do you kind of see a trend of that throughout all of South America with other scientists, or are you just studying Brazil?
I'm just studying Brazil, and if we go back to this graph, so Argentina, everywhere in South America is trending toward deforestation, particularly for agricultural stuff. Argentina is converting a lot of land to soy. Bolivia is starting to. Some of it's for palm oil. Peru, and for mining. Mining is the other big reason that the deforestation happens on a large scale. But the thing that I'm worried about most in Brazil is, never mind. If you drew, so deforestation had been decreasing since 2016, up until about 2014, 2015. Then there was a big change, their president was impeached. And the new guy in power, Michel Temer, named this guy Blair Maggi, who is from the stage in most of my work. He's won the Golden Chainsaw Award from Greenpeace because he's like so good at deforesting. They named him Minister of the Environment. Not great. So what's been happening actually now, the other thing is Brazil's been in a huge economic recession. And the one thing that they would always say there is there's no recession in agriculture. Agriculture was the only thing keeping Brazil afloat from the recession in 2013. They're even worse now. But the ag lobby is huge there also. So people, and there's a new election coming up, but it's actually pretty terrifying if the guy who is predicted to win is going to win, because he's like, we're gonna deforest the whole Amazon. His name's Bolsonaro. You should look up Brazil stuff. It's actually kind of crazy. But basically, farmers are deforesting, assuming that they will be given lenience and they won't be penalized if there's a political party shift in office. So we've actually seen in Brazil also deforestation rates go up, where beforehand, when it was the progressive, the PT was in power, they were really champions of environmentalism. They were sort of like, Brazil is going to be the model of sustainable development. We're going to show you how. I mean, I can get pushed with deforestation in the Cerrado, but deforestation rate in the Amazon did go down. And people are being penalized. Like, if they caught you deforesting, they monitored deforestation with satellite data, they would fine you. But now, once the regime shifted, the new Michelle Temer was like, you're not going to get fined. So that gave farmers like, oh, keep doing this and we're not going to get fined. And then other places in South America saw Brazil's rise. And we're like, this is a model that might work, right? And if you can't, I talk to farmers all the time. And I'm like, this could affect climate in 100 years. He's like, but I get paid next week, right? And then also, he's like, you guys cleared your whole country, and now you're telling us what to do? Like, that's money. Those trees are money for me and my family. And you're just like, okay, right? Like, how you can't, it's not my place to say, please, right? Do you understand? It's complicated. But you do see it rising everywhere.
Is there indigenous pushback? Sorry.
Indigenous?
Yeah.
Yeah, so actually it's really, generally it's the farms that I work on are these big multinational corporations. It's really not a great situation. There's a lot of violence between indigenous communities and farmers, and also what happens with indigenous communities and with just small farmers, they wake up and all of a sudden there's a fence in their yard because land titling there is not really secure and it's different than here. So they'll wake up and it'll just turn out like the Maji Corporation or Bungie or Louis Dreyfus or whatever just bought a bunch of land, just drew a line on a map, and the fence appears. There's a lot going on. It's an interesting place to work.
Okay, so let's stay feel free to grab more pizzas. There's some left. If you haven't signed in for advance or climate stats, please do. It's sitting right up here by Francis.
Yeah.
That was really bad. It's a lot.
Hi.
Hi.